Hiroshi Wada to join us. And so Dr. Hiroshi Wada is the head of the conservation science, section of the Tokyo National Museum. He has been working there since 2000 as a researcher on preventing conservation, and in recent years he has also conducted research on the relationships between the response characteristics of cultural property materials to vibrations generated during transportation and the accumulation of fatigue, as well as on the application of digital technology to museum activities. Thank you.
Thank you for the kind introduction. I'm Hiroshi Wada, came from Tokyo, Japan. I appreciate the opportunity to present at such a wonderful conference. Currently, I am one of the very few researchers in Japan focusing on the transportation, environment, or cultural properties. I participate in this conference to broaden my international perspective and gain cutting-edge insights. The title of my presentation is as follows. As you know, when measuring vibrations during the transportation of cultural properties, we use acceleration data loggers. The 4 key parameters in the measurement protocol are shown here. Sampling frequency, wake-up interval, signal trigger level, frame size. In the past, due to the limited memory capacity of data loggers, we had to carefully optimize the settings to capture the overall characteristics of transportation. However, with the increased amount of memory available today, the need for fine-tuning has decreased. It is now possible to continuously record vibrations throughout the entire transportation process. But it is important to note that this approach significantly increases the data volume. We conducted continuous vibration measurements during transportation. I will now introduce a case study from these measurements. As shown here, this was a relatively long distance example of cultural property transportation in Japan. The transportation took 5 days and 4 nights using both trucks and ships. The transported cultural property was glass plate negatives, as shown here. Here is an overview of the measurement. The sampling frequency was set to 800 Hz. We created a dummy box filled with weights matching the weight of the glass. Data loggers were installed both inside the dummy box and on the truck bed. The total transportation time was 89 hours. Here is the setup of the data loggers. You can see how left figure shows in the dummy box, and right figure shows on the truck bed. Here is the packaging setup. In Japan, we often use the neutral paper box, and this is also for storage box. As shown, the packaging consisted of an inner box and an outer box. The inner box was wrapped with natural cotton and placed inside the outer box. In fact, a large number of glass plate negatives were transported. They were loaded onto the truck which departed from Tokyo. Here is the data analysis process. Since the measurements were taken at 800 Hz, the collected data became very large, reaching about 3.6 gigabytes in total size. Using the free software provided with the data logger, we converted the data into several split MATLAB format files. The files were split to avoid processing interruptions caused by the large data size. After that, I merged the split files vertically using code 1. Next, using code 2, I specified channels and time periods and performed PSD, power spectrum density calculations. Finally, with code 3, I visualized the data. While some manual operations were involved, and the use of these codes enabled semi-automation of the analysis. As a result, even with the large volume of data, the analysis could be completed in a relatively short time. I will now explain some of the innovations we applied in this analysis. As you know, FFT, fast Fourier transform analysis was necessary to decompose the vibration data into frequency components. In FFT analysis, the vibration data must be divided into predetermined frame sizes. And in FFT analysis, a window function is applied at each frame to create a periodic pattern in the vibration. Therefore, the window function forces the vibration at the end of each frame to be weakened. The problem is that if important vibration information exists at the edge of the frame, it might be lost during this process. To solve this problem, overlap processing is used. Here is an overview of the overlap processing. In this time, I fixed the overlap rate at 90%. And I carefully considered the selection of the frame size. So after calculating the PSD for each frame, the frame size was determined based on the appearance of the PSD. For example, with a frame size of 2 seconds, it appears as this. The top graph shows the time variation of the PSD with frequency on the vertical axis. The bottom graph shows the time variation of the vibration with acceleration in g on the vertical axis. Let's see how the results change. We adjust the frame size. It becomes clear that there is a trade-off between time resolution and frequency resolution. So based on this examination, I conducted that frame size of 7 seconds was appropriate. This decision was made because the balance between frequency resolution and time resolution appeared visually optimal, although it was not based on statistical analysis. Here is the data from the trackbed. And here is the data from inside the box. Here is a comparison over a short Please look at the section enclosed by the red dotted line. Red dotted line. Frequencies above 50 Hz were not present inside the box. Here is a comparison in the form of PSD plots. It is clearly visible that the high frequency components inside the box are significantly lower. And here is a comparison with the averaged PSD values for better clarity. It is evident that the high frequency components inside the box are smaller. On the other hand, frequencies around 10 Hz were amplified inside the box compared to the trackbed, the blue dotted line squares. Here is the PSD in the box divided by the PSD in the trackbed. In other words, it shows the ratio of the vibration of the trackbed transmitted into the box at each frequency. Both figures have frequency on the horizontal axis and the transmission ratio on the vertical axis. The left figure uses a logarithmic scale for the vertical axis, while the right uses a linear scale. It is clear the transmission ratio was high for frequencies around 10 Hz. To confirm this phenomenon, we conducted experiments after the transportation. We replicated the same packaging used during transportation. Packing box is being secured to the vibration table and input sine waves from 2 Hz to 500 Hz and random waves. This random wave used international standards. We also used a modified version of the international standard random wave using this transport data.
There's 5 minutes.
Additionally, we measured each packaging material individually to assess their response to vibrations from materials and natural cotton wrapped with paper. Here are the experimental results. The left figure is the experimental results. This is a result of an experiment using sine waves. And the figure on the right shows the measurements recorded during transport. It was confirmed that the resonant frequency exists around 10 Hz. We identified the resonant frequency of the box AC. Here are the experimental results for the packaging material used. The discussion of these results is still ongoing. I suppose that the resonant frequency of the entire box is determined by the combination of the individual vibration characteristics of each material. Here are the conclusions. We semi-automated the vibration data processing, and we optimized the frame size for vibration analysis. We confirmed the characteristics of the box through vibration experiments. However, there are still significant challenges to address. It is essential to identify which types of vibrations the cultural property being transported is particularly sensitive to. I look forward to learning more from the research results you will share with me at this conference. Thank you for your attention. That's it.
So I'm going to invite now the third speaker, Francis Kelly, from the Stiftung Musisches Museum in Berlin.